Welcome to AERO 1020, Theory of Flight, presentation number 5 on airspeeds and altitudes. Before we move on to discuss the different altitudes and different airspeeds, let's just review briefly atmospheric pressure. So what are the measures of atmospheric pressure and what are the standard sea level pressures? Well, if we measure sea level pressure with a barometer, it is 29.92 inches of mercury. The temperature at sea level is 15 degrees Celsius. We can also measure that in millibars. The standard atmospheric pressure at sea level in millibars is 1013.2. And we can measure the temperature in Fahrenheit, which would be 59 degrees Fahrenheit. Another measure of standard pressure would be in pounds per square inch, and standard atmospheric pressure at sea level in pounds per square inch would be 14.7 pounds per square inch. So what is the altimeter setting? Well, the Pilot's Handbook of Aeronautical Knowledge defines altimeter setting as the station pressure reduced to sea level. But remember, the altimeter setting is only accurate in the vicinity of the reporting station. The altimeter setting is not the pressure outside the airplane, unless the airplane is at sea level. And very simply, altimeter setting approximates the barometric pressure at sea level at that point in time, at that place on the planet. So what exactly does an altimeter measure? Remember, an altimeter measures air pressure. Now we can measure altitude in several different ways. The first one is absolute altitude. Absolute altitude is simply the distance above the terrain or above ground level. True altitude is the distance above sea level, and it's denoted in feet above MSL or mean sea level. And you can see true altitude on aeronautical charts for obstacle and airport heights. Indicated altitude is simply the altitude that's read directly from the altimeter when it's set to the local altimeter setting, and it approximates true altitude. Remember, true altitude is the height above mean sea level, and it's used by all aircraft flying below 18,000 feet MSL. Pressure altitude is the altitude that's indicated when the altimeter is set to the standard pressure at sea level, or 29.92 inches of mercury. It's required to be used by all aircraft flying above 18,000 feet MSL, or mean sea level. And these are called flight levels. At 18,000 feet, the flight level is 180. Flight level 180. Pressure altitude is also used for aircraft performance calculations. Here's a pressure altitude table used to convert indicated altitude to pressure altitude based on the local altimeter setting. Notice that at the standard pressure of 29.92 inches of mercury, there's a zero adjustment. And if the altimeter is greater than 29.92 inches of mercury, we have to subtract to convert indicated altitude to pressure altitude. If the altimeter setting is less than 29.92 inches of mercury, we have to add to make the correction. Density altitude is simply pressure altitude corrected for non-standard temperature. And remember, density altitude affects the aircraft's performance. High density altitude means low density air, and that leads to lower performance. Low density altitude means high density air, and that leads to better performance. There's a density altitude chart in the Pilot's Operating Handbook for the Diamond DA-40 on page 5-6 that allows you to convert pressure altitude to density altitude based on outside air temperature. Now here's a picture of the density altitude conversion chart from the Diamond DA-40's Pilot Operating Handbook. And the great thing about these charts is they usually include an example to help you learn how to use the chart. And that's indicated below the chart here. They start out with a pressure altitude of 900 feet, and they draw a straight line from 900 feet pressure altitude over to the temperature of 21 degrees C. And where these two lines intersect, they begin following this line parallel down to the next reference line. And at that point you can see the density altitude. They started with a 900 foot pressure altitude, and at 21 degrees C they ended up with a density altitude of 1,800 feet. So the density altitude in this case is high compared to the pressure altitude. And that makes sense because the temperature of 21 degrees C is much higher than the standard temperature at that pressure altitude, represented by this line. You can see the standard temperature at that pressure altitude is about 13 degrees C. So let's review the different types of altitude. The first one we discussed was indicated altitude, and that's just the altitude that's read off the altimeter when the altimeter is set to the local altimeter setting. The next one was pressure altitude. Remember, pressure altitude is the height above sea level or mean sea level when the altimeter is set to the standard pressure at sea level of 29.92 inches of mercury. The next one was density altitude. Density altitude is pressure altitude corrected for non-standard temperature. And true altitude is the actual distance above mean sea level. Finally, absolute altitude is the altitude above the surface, or above ground level, AGL. Now, aviation is full of acronyms to help you remember things. There's an acronym to help you remember the different types of altitudes: TAPED, T-A-I-P-D, true altitude, absolute altitude, indicated altitude, pressure altitude, and density altitude. Remember, true altitude is height above mean sea level. Absolute altitude is height above ground level. Indicated altitude is the height measured by your altimeter when it's set to the local altimeter setting. Pressure altitude is the height that is indicated by the altimeter when you have the standard pressure set of 29.92 inches of mercury. And density altitude is pressure altitude corrected for temperature. Here's an illustration of the different types of altitudes. The aircraft on the left at 35,000 feet has the standard pressure set in the altimeter of 29.92 inches of mercury. So that 35,000 feet is 35,000 feet above the standard pressure datum of 29.92 inches of mercury. The aircraft on the right has a local altimeter setting of 30.10 set in the altimeter, and that aircraft indicates an altitude of 3,000 feet. Remember, that's 3,000 feet mean sea level, or above sea level. 30.10 is the pressure at sea level. So that aircraft is showing its altitude above sea level. Here's another illustration to help you understand different altitudes. The aircraft on the right is sitting on the ramp at an airport that is 360 feet above sea level. And since it has the local altimeter setting of 30.10 set in its altimeter, the altimeter is indicating the height above sea level. Because again, 30.10 is the altimeter setting or the pressure at sea level. So remember, it's very important to set your altimeter every so often on a flight to the local altimeter setting, because the pressure can change as we fly from one area to another. If we fly from a high pressure area to a low pressure area without resetting our altimeter will indicate that we're higher than we actually are. So our altimeter will indicate higher than our true altitude. So the saying is, high to low, look out below. Your altimeter says that you're higher than you really are. The same problem with our altimeter exists for different temperatures, and unfortunately we can't adjust our altimeter for change in temperature, so we just have to keep this in mind. When you fly from an area of hot weather to an area of cold weather, the same thing happens. Your altimeter indicates that you're higher than you really are. So here is a cold temperature error table issued by the International Civil Aviation Organization, or ICAO. And as you can see, you have different temperatures on the left-hand side and different heights above the airport in feet at the top. So let's look at 1,000 feet above the airport at minus 10 degrees Celsius. The error in your altimeter would be as high as 100 feet. So your altimeter would indicate that you're 100 feet higher than you really are in that situation. Now, before we move on to discuss the different types of airspeeds, let's take a look at the airspeed indicator. We discussed the pitot-static system in the last presentation, and we went through the construction of the airspeed indicator. Remember that the airspeed indicator is connected to the pitot tube and also to the static port. And remember, the airspeed indicator is the only pitot-static instrument that is connected to both the pitot tube and the static port. The other two, the vertical speed indicator and the altimeter, are only connected to the static port. Now, the inside of the airspeed indicator includes a diaphragm which receives pressure from the pitot tube as the aircraft moves through the air. That pressure is called total pressure. That's dynamic pressure, or the pressure of moving air, plus static pressure, or the pressure of still air. The inside of the instrument casing is filled with static pressure from the static port. So the movement of the diaphragm as the aircraft moves through the air drives these pinions, which converts the movement into an airspeed on the face of the instrument. Now, the Diamond DA-40 is a technically advanced aircraft with a glass panel, and the airspeed indicator is on the left side of the primary flight display. And instead of the analog round dial, you have a digital readout on the primary flight display. But the information displayed is obtained in the same way as it is on the analog instrument. In other words, dynamic pressure, total pressure, is compared to static pressure, and the difference is converted into airspeed. So what exactly does an airspeed indicator measure? Well, it measures pressure. It measures the total pressure, which is dynamic pressure plus static pressure. And it subtracts static pressure from the total pressure, which just leaves dynamic pressure, which is converted to airspeed. So the first type of airspeed is indicated airspeed. And that's the speed of the aircraft that's shown on the airspeed indicator. It's calibrated to reflect standard atmosphere, and it's not corrected for any airspeed system errors. Indicated airspeed is used for performance speeds in the pilot's operating handbook. Now, calibrated airspeed is just indicated airspeed corrected for position and instrument errors. And the reason for that is the way the instruments are constructed on the aircraft. The pitot tube is fixed on the underside of the left wing of the aircraft. So when the aircraft is flying at slow airspeeds and maintaining a high angle of attack to maintain altitude, the sample of dynamic air pressure flowing into the pitot tube is not as great as it would be at higher airspeeds. And so because of that, there's an error. Calibrated airspeed is actually higher than indicated airspeed when the aircraft is flying slow. Then the error disappears closer to cruising speeds, and that higher airspeeds, calibrated airspeed is lower than indicated airspeed. And you can see this on an airspeed calibration chart in the Diamond DA40 Pilot's Operating Handbook on page 5-3. Now here is the airspeed calibration table from the Cessna 172 Pilot's Operating Handbook. Instead of a chart, Cessna puts out a table to show the difference between indicated airspeed and calibrated airspeed. As you can see, with flaps up, indicated airspeed of 50 knots results in a calibrated airspeed of 56 knots. So again, calibrated airspeed is higher than indicated airspeed at slow speeds. And then it disappears right around 80 and 90 knots. And then above 100 knots, indicated airspeed, calibrated airspeed is lower than indicated airspeed. Now that doesn't have anything to do with the pitot tube. That is due to the pressure of the air outside of the static port. Remember, as the aircraft flies faster through the air, that acceleration creates lower pressure outside of the static port. So that's why at high airspeeds, calibrated airspeed is actually lower than indicated airspeed. Now equivalent airspeed is just calibrated airspeed corrected for compressibility, or as it says in this slide, adiabatic compressible flow for a particular altitude. Equivalent airspeed is equal to calibrated airspeed in a standard atmosphere at sea level. Because it's not significant for an aircraft that flies below 200 knots, it's not something that we need to be concerned about flying in an aircraft like the Diamond DA40 or the Cessna 172. Equivalent airspeed only becomes a problem when you're flying above 200 knots. Compressibility also becomes a problem at higher altitudes in addition to airspeeds above 200 knots. As you can see, below 200 knots at the lower altitudes, there's very little difference between calibrated airspeed and equivalent airspeed. But as you get above 200 knots at the higher altitudes, for example, let's look at 30,000 feet at, let's say, 350 knots, the difference between calibrated airspeed and equivalent airspeed is greater than 20 knots. It looks like about 22 knots. So equivalent airspeed is actually 22 knots greater than calibrated airspeed at that altitude and at that airspeed. Now, true airspeed is the airspeed of the aircraft relative to undisturbed air. And true airspeed is equal to equivalent airspeed multiplied by the square root of the density at mean sea level over the density at the aircraft's altitude. Now we can get the density ratio by looking at the ISA table, the International Standard Atmosphere table. And as you can see, at 0 feet altitude, the density ratio is 1. But as we climb, that changes. At 5,000 feet, the density ratio is 0.8617. So with the density ratio from the ISA chart, we can now figure out what the density is at 5,000 feet by taking that ratio and multiplying it by the density at sea level, 0.00238. So 0.8617 times 0.00238 is 0.00205. That is the density at 5,000 feet. Now we have the density for 5,000 feet of 00205. We can calculate the true airspeed by multiplying the indicated airspeed times the square root of the density at sea level, 0.00238, divided by 0.00205. And when we do that, we get a true airspeed of 108 knots. So as you can see, true airspeed increases as the density decreases with increasing altitude. So for increasing altitude, constant indicated airspeed means a higher true airspeed. For increasing altitude, a constant true airspeed means a lower indicated airspeed. And there are different methods to determine what our true airspeed is. There is a way to determine that on some analog airspeed indicators. The Diamond DA40 primary flight display actually calculates your true airspeed for you. There is a chart in the pilot's operating handbook on page 5-13 to help you determine what your true airspeed is. You can use your flight computer, or we can use the rule of thumb. The pilot's rule of thumb is to add 2% to the indicated airspeed for each 1,000 feet above mean sea level. Here is an indicated airspeed and true airspeed chart that you can use to determine your true airspeed. As you can see, the true indicated airspeed is at the top, and below that you see the different true airspeeds based on altitude. So at 8,200 feet, true airspeed is 145 knots, when indicated airspeed is 124 knots. Now, some airspeed indicators, like the one pictured on the left, allow you to convert indicated airspeed into true airspeed by lining up your temperature at altitude with your pressure altitude. You do that by twisting this dial on the right-hand side. That also moves this dial here on the lower left-hand side of the airspeed indicator. This is an old airspeed indicator that indicates miles per hour on the outside. And as you can see, in this case, the indicated airspeed is about 173 miles per hour, but the true airspeed is about 203 miles per hour. Now here is a cruising airspeed chart from the Diamond DA40 Pilot's Operating Handbook. And as you can see, like the other charts, it comes with an example at the bottom to help familiarize yourself with how this chart works. It starts with a pressure altitude of 5,000 feet, and you start on the left-hand side at 5,000 feet, and you draw a straight line to the right until you reach the temperature, in this case 15 degrees C. Where those two lines intersect, we start to follow this line down to the next reference line, and then we draw a straight line from there to the right to our percent of power line. From that point where those lines intersect, we draw a straight line down to our true airspeed of 118 knots. So again, we have an acronym to help us remember all of the different airspeeds. It's ICE-T. I for indicated airspeed, which is just the airspeed that you read off of your airspeed indicator. C for calibrated airspeed, which is indicated airspeed corrected for instrument and position error. E is for equivalent airspeed, which is calibrated airspeed corrected for compressibility. And T is for true airspeed, the speed of the aircraft relative to the atmosphere. We also have ground speed. Ground speed is not an airspeed, but the ground speed is the speed at which we're moving over the ground, which can be different from our true airspeed based on the wind. Here's a link to a video about true airspeed. You may want to watch this to get a better understanding about what true airspeed actually is. It's not mandatory, but highly recommended. So remember, the airspeed indicator is color-coded. The white arc on the airspeed indicator is the flap operating range. That's the range of speed that you can operate with your flaps extended. The green arc is the normal operating range. The yellow arc is the caution range. You only want to operate in that range in smooth air. And then the red line is the never exceed speed. Now remember, when you hear the words bottom of the white arc or bottom of the green arc, that means the lowest airspeed on that arc. Okay, so this is the bottom of the white arc. This is the top of the white arc, not the other way around. So at the bottom of the white arc is VSO. VSO is the stall speed in the landing configuration, with the landing gear down and the flaps down. At the top of the white arc is VFE. That is the maximum speed with your flaps extended. At the bottom of the green arc is VS1. That's the stall speed in the clean configuration. And then at the top of the green arc, or the highest airspeed on the green arc, is VNO, normal operating speed, or maximum structural cruising speed. And then at red line, or at the top of the yellow arc, is the never exceed speed, VNE. So again, the flap operating range is the white arc. At the bottom of the white arc is VSO. At the top of the white arc is VFE. The green arc is the normal operating range. At the bottom of the green arc is VS1, stall speed in the clean configuration. At the top, at the highest airspeed on the green arc, is VNO, maximum structural cruising speed. The yellow arc is the caution range. You only want to fly at speeds in the yellow arc in smooth air. At the bottom of the yellow arc is VNO. That's the maximum structural cruising speed again. So that's at the bottom of the yellow arc, at the top of the green arc. And then at the top of the yellow arc is VNE, or the never exceed speed. Remember that the red line is VNE, and that is the maximum speed that the airplane can be operated safely. Exceeding that speed can cause structural damage or even structural failure of the aircraft. Now, one speed that isn't represented on the airspeed indicator is known as maneuvering speed, or VA. That's the maximum speed at which you can make full and abrupt control movements without stressing the aircraft structure. You want to fly at or below this speed in turbulence. So here's another representation of the analog airspeed indicator. The Diamond DA40 with the primary flight display has color codes as well on the digital readout for airspeed, but get to know the different color codes, what they represent, and what the bottom and top speeds represent on each one of these color-coded arcs. Now, we looked at an airspeed indicator, an older analog airspeed indicator that had both knots and miles per hour. So how do we convert knots to miles per hour or miles per hour to knots? Well, first we need to figure out how many feet there are in a statute mile. Miles per hour is based on a statute mile, and there are 5,280 feet in a statute mile. How many feet in 1 nautical mile? There's 6,076 feet in 1 nautical mile. So a nautical mile is actually further or longer than a statute mile. So how do we convert 150 knots to miles per hour? Well, 150 nautical miles per hour is how many feet per hour? We know that 1 nautical mile is 6,076 feet, so we multiply that by 150 nautical miles to get 911,400 feet per hour. How do we convert that to miles per hour? Well, we know a statute mile is 5,280 feet. So we take 911,400 feet divided by 5,280 feet to get 172.61 miles per hour. So 150 knots is 172.61 miles per hour. So that's the end of presentation 5 on different airspeeds and altitudes. The next presentation, presentation number 6, will be on Newton's laws.